Hello guys, welcome to this tutorial. In this tutorial we will speak about memory and how we can detect which parts of memory we can use, which are reserved. In the real mode we have access only to 1 megabyte of memory, even less than that. But in protected mode we can use memory up to 4 gigabytes, and in long mode much more than that. So we need to understand in protected and long mode which parts of our memory we can use. In real mode we have access to BIOS interrupts, and we're going to use this interrupt to understand which parts of our memory we can use. How to get a memory map, basically, a table of our memory entries. So to do that we are going to use interrupt 0x15. We are going to use 32-bit registers. You might think that we are in real mode. We can use until 16-bit registers like AX, CX, BX. How can we use 32-bit registers? We can use 32-bit registers in real mode. We can use them to store things and print things, but we cannot use them to jump to a memory address above 1 megabyte. That we cannot do. And because we are going to deal with 64 and 32-bit values, we need to use 32-bit registers. So we are going to set E820 hexadecimal in the EAX register, and we are going to set this value in the EDX register. If we check it and we make it into ASCII, we will see that this value converts to SMAP. SMAP, when we put it in the EDX register, it will specify the format of the memory entry. That we will explain soon. At start, EBX should be 0. And in ECX we are going to set the values for how many bytes our result buffer will be. And in ESDI, our buffer will be stored there and our result will be there. Basically, at the extra segment with the DI as offset. If everything goes well, our carry flag will be clear. Our EAX register will be what the EDX register was before, our SMAP, and our buffer will be filled, and the EBX will be 0. So, let's explain now about the memory map structure. Our memory map will be with 64-bit entries. Basically, our base address is going to be 64 bits, our length is going to be 64 bits, our type will be 32 bits, and if we have an ACPI 3.2 entry, basically with 24 bytes instead of 20, we will have extra information in these 32 bits, basically if we should ignore this entry or not. I have written it with segmentation model here, and you can see that at ESDI we have our base address, plus 4 we have the high bits of our address, and we can keep going, you can understand. And I have also written it in that way, the 24 bytes in total, how they are distributed. Now, I have already written the code for this lesson because the algorithm is quite difficult to understand and it's complicated. So I prefer to use this time to explain this algorithm than just write it. So let's go and explain our code. I have written a lot of comments that will help you, and I will post an article from osdev in the video description. So if you don't understand it from the beginning, I suggest to take it step by step, read each comment very well, read the article, and of course if you have any questions, put them in the video description. I will be glad to help you. One more change that I did is that I put the stack pointer at 0x7000. I could have left it at 8000 because the stack grows downwards, as we know, but just in case I set it at 7000. Maybe later we will put it back at 8000. At 8000 I put the memory map entity count. Let's go and let's start explaining our code. So, first we will move 8004 in the DI register. Why this value? Because this value doesn't contain anything else. It doesn't bother us somewhere. It could be any other value, basically. Okay, not any other value, but it could be many values there. You can put 9004, 9000, anything you want, basically, as long as it doesn't interfere with something. I chose 804. In the article that you will see, they chose the same. We make EBX into 0 and the BP into 0. Our EBX needs to be 0 for our code to start, and the BP will contain the entry count. So we make it into 0. We put our SMAP in the EDX register and the E820 in the EAX register. Basically the function to get the memory map. Now we force a valid ACPI 3.x entry. How we do that? Let's see here. We go at this offset here, at this memory here, and we set a D word, basically 4 bytes, 32 bits into 1. And then we initialize the extended attributes to have this extra information. Basically this will tell us if an entry is volatile or it's we should ignore it or not. We will see. Let's continue. We move 24 into ECX. Basically we say that we want a buffer result of 24 bytes because the extra 4 bytes will be the extended attributes, and we use our interrupt finally. Now if the carry flag is set, means something went wrong, we have failed. Some BIOSes damage this value here, they change it, so we set it again. And on success, it should contain, EAX should contain this value. If it's not, we have failed again. If EBX is 0, means we have finished and we have only one entry, means something went wrong, we have failed again. Otherwise, we jump here. If the ECX is 0, we skip this entry. It's an invalid entry length. It means our length is 0, basically. So we don't need it. It's invalid. Then we compare CL with 20. Basically, we want to check if we have these extended attributes, this information. If it's below, if it's equal or below 20, we will jump to this label here. Let's jump here and we'll explain the other situation after that. Here we're going to get the lower 32 bits of the memory region length, and we're going to OR it with the high 32 bits of the memory region length. If we OR them together, we are going to get the 64 bits of the length. And someone could ask why the highest bits are in +12 and the lowest at +8, because we have a little endian system. I will post an article about it in the video description. Now, if the length is 0, we skip it. We increment the BP, our count, and we move the next entry into our buffer, basically 24 bytes after what we did before. Now, the other situation, basically we were here. Now, in this situation, if the bytes are more than 20, we test the bit basically of the extra attributes. If bit is clear, it means the entry should be ignored. If the entry should be ignored, we skip it and we jump here. Here we test EBX. If it is 0, our list is complete. Otherwise, if it's not equal to 0, we jump to our loop. With our loop, we do what we did before, basically. We set EAX again to this value. We want to get basically the next memory entry. So we set this value here. We force a valid ACPI 3.x entry. We ask for 24 bytes again, and we call BIOS interrupt 15 again. If the carry flag is set, it means that we have already reached the end. And otherwise, we set this value again, the smap, like we spoke about before. Okay, now what happens at the end here? We move into the memory position of our map entry, the count, and we set it into 0x8000. Basically, our entry count, we set it into 0x8000. We have set it before, if you don't remember. Map and 0x8000. And then we clear the carry flag, because there is the carry flag at the end if we reach the end. So this is the code, basically. I know it can be difficult. You should read the comments and read the article that I will send, and it will help you understand. Now, we need to print the memory map. I will show you actually. If I press M, this is the memory map. As you see, these are hexadecimal values. We will explain in a following video about some things about the memory map, but now we need to reach the point to have it. We cannot print hexadecimal values as we do with strings. No, we have to convert it into ASCII first. I have already created a routine here called printhex.asm, and I have also added an example here of what we do to make them into ASCII and print them. Basically, we save all general purpose registers just for safety reasons, and we want to print 8 hex digits, 32 bits. So we copy the value to be printed from EAX to EBX, and we start our loop. Basically, the first thing that we do is rotate left. From this, it's just an example, we go to this. Basically, we rotated left. We rolled by 4 bits. Then we move BL into AL. Basically, this part here. We move it into AL. Then we end it with 0x04. Basically, now after we end it, we are going to take this 0x01, only the last 4 bits from the 8 bits. We check if it's less than 10. If it is less than 10, we just print digit. Basically, we add character 0 to it. Why do we add character 0? Let's see here. Here we have our ASCII table. See, for example, we have hexadecimal 0. It is at value decimal 0, octal 0. Here we have our, where is it? Character 0. Here, character 0. How much is it in decimal? 48. If we add 48 to 0, we will reach 48 here. Let's take another example. Let's take 2. 2. If we add 48 to it, we will reach 50. And this will be the character 2. That is the process that we do. If we are below 10. If we are above 10, we need to add into AL character A minus 10 to print A to F. We convert basically 10 to 15 to A to F. And we jump to print hex digit here. We just print the digit. I have this example here. It will help you understand the process. This is the way we print a 32-bit hexadecimal value or 8 hex digits. So I will close this file and we are going to see how we are going to print it. So how to display our memory map. We are going to do what we explained until now. We are going to call this routine here. Then we are going to move the memory map string into ASCII. The memory map string basically it's just a header, memory map for our table. So then we're going to call print string. We're going to move 8004 into DI and we're going to move the number of our memory map entries into the CX register. And now for the printing. Let's compare CX to 0. If the CX is 0, we jump back to get input from user. Then we move into ASCII the base address string. Let's see it. The base address string is just base address. It just helps us understand the information. Then we call print string. Into EAX we move the first upper 32 bits of our address and we call print hex. Then we do the same for the lower 32 bits. Then we print a string about the length, basically length of region. We call print string and then we print the upper 32 bits of the length. We print hex and then we print the lower 32 bits of the length. Now we reach the type. We move the type string into the ASCII register, basically just the word type. We call print string and we put here the 32 bits of the type into EAX and we print it. We add 24 into DI to move into the next entry. We decrement CX and we jump back at the beginning at print entries to print the next one. So that is our code basically to print it. Here I have just added this. If we compare AL to M, basically to if we press M, we display the memory map. Otherwise, command not found, like we did before with D. This is for this video today. No, there is one more thing. I want to explain something here. In the article that you should read about detecting memory, you will see this here. Wait, I want to check. Yes, the types. As you see here, when I run our program and I press M, you see type 1, 2, 2, 1, 2, 2 for each entry. Let's quit. Type 1 means usable, type 2 means reserved, type 3 ASCII reclaimable memory, ASCII NVS memory, and type 5 is area containing bad memory. We are going to use everything that we see with type 1, but it's too early to speak about it right now. We should detect it in real mode, but we're going to use these memory addresses in protected mode. Probably, I think, I'm not sure yet, but we will do it while writing C code. In protected mode, we will write some assembly, but I think we will continue with C from that point forward. But I don't know, maybe we will continue more in 32-bit assembly. We'll see. So, if you have any questions, please put them in the comments. I will be glad to help you. If you like this video, please like and subscribe. And thank you for any informational comments, any feedback you write to me is very appreciated. Thank you very much. See you soon.